My name is Dustin White, and I'm currently the Director of Digital Technologies and Fabrication at the New York Institute of Technology, School of Architecture and Design, an adjunct professor, and I also have my own practice. First, I would like to thank you for the invitation. It looks like an exciting program that you have assembled, and I'm looking forward to contributing and presenting my work today. The title of my lecture is Material-Based Computational Design Strategies. But before jumping in, I think it's important to contextualize who I am and my background. As Director of Digital Technology and Fabrication, I'm managing our fabrication labs at our two campus locations in New York City and Long Island, where I'm overseeing multiple full-time staff and labs that were recently renovated to include advanced 3D printing labs with ceramic, carbon fiber, large format plastic and resin printing, a robotics lab, a laser lab, and traditional analog and woodshop. As an instructor, I have 12 plus years teaching in multiple institutions. I teach across the undergraduate and graduate programs, and I've taught and coordinated 14 different courses ranging from design studios, visualization and modeling, computation, digital fabrication, interior design, furniture design, and proto lab in the Design Morphing online master's program. I also include the work produced from my students, since the work they produce also has an influence on my own research and practice. In my practice, the work varies in scale, technique, method, intent, and fabrication processes, but is fascinated with thinking through material-based computational design strategies. I become more interested in creating interactive work either through technology or sensorial experiences. For the 2021 Biennale, our installation brought together stone and nature in a lively, dynamic narration to inscribe a public open room. The installation CRISPR turns spatial resonances into a stage for social encounters, an emotional observation point of the beauty and power of water, still hidden by walls in the extensive complex of buildings. It is a sensorial immersion into expectation as a reflection on the passing of time and the uniqueness of an inspiring place that went through a history of transformations. The Arsenale, one of the landmarks of Venice. CRISPR traits are revealed by its rules and at times latent principles which, if written computationally, are generally nonlinear geometries, interchangeable, as well as non-adaptive functions relationships. I'm engaged in exhibition design. In the example, a showroom build for Meljac, a French ship switch manufacturer, luxury and bespoke furniture, which we'll see more of as we go along. And that brings me to the lecture, which will outline projects from the last 5 years of a research-based design practice with an interest how technology, craft, and materials come together in ways that explore the boundaries between design, architecture, and other disciplines, specifically the pedagogy of material-based computational strategies, supporting the integration of form, material, and structure by incorporating physical form-finding strategies with digital analysis and fabrication processes. In this approach, material often comes before shape, the material explorations as the premise for making and fabricating, and design decisions that emerge from the results of the material experiments and testing. The work produced by my students and by myself seeks to challenge digital technologies and fabrication to further the relationship of material to machine and material to design, with the intent to develop and employ novel software techniques that aid in the translation from the virtual world to the physical medias we engage through craft and technology to hybridize design and making. I'm very much interested in beginning a project with a material and machine process before a formal or shape-making process, and it's critical that I'm constantly making and testing prototypes in the studio. So some of the examples we see in here are laser cutting examples, vacuum forming, 3D printing, CNC machining. I'm really trying to utilize all the different processes we have in our labs and at our disposal. I'm going to go and preface an older project because it really laid the groundwork for most of my projects today. The first project will feature soft and light materials and will transition into more permanent and substantial materials. I'm not interested in complicated things, but I am interested in complex things. I would like for the work to be intelligible so people can engage with it. The strategy is to layer on complexity so people understand it. Infinity Helmet was a commissioned project for an outdoor art installation event, and the organizers were seeking ideas to resolve wayfinding and ways to distribute artist information and educate the community. An idea was developed to challenge the normative event kiosk and information point as this wearable device. Infinity Helmet was designed as a small-scale architectural experiment or wearable prototype that creates an immersive, virtual, and physical experience, and was intended to interact with users and users interact with it. There were multiple of these objects produced, and they were all linked together and distributed throughout the event. On a technological level, Infinity Helmet challenges the two-dimensional matrix of a standard screen display. Infinity Helmet wants to blur the lines of these ubiquitous rectangular screens into a spatial immersive environment through its material and formal qualities. The helmet is embedded with an iPad, LEDs that are responsive to motion and sound, and another of other tech. Utilizing a set of polygonal shapes which serve as a source geometry for the design and help define the installation's overall topology, the result was stitched minimal surface geometry with apertures or framed openings. To rationalize the minimal surface, this is where I became interested in how we could produce these types of geometries efficiently, and we've developed a method of projecting a hexagonal mesh netting over the geometry, and through other computational means, we're able to create, in this case, 400 discrete planar hexagonal panels. At that time, and even now, there are really not many accessible software that have native tools for unrolling or flattening panels through an automated process. The challenge when unrolling complex or regular hex-shaped panels is they will overlap with itself in 2D. So that added a complexity to split the panel in half and create an additional tab connection. So now we went from 400 panels to 800 panels. But on the other hand, I learned how to be organized and split models into color-coded parts and labels in 3D and 2D. The interesting thing here is that we are seeing about 80% of the drawings produced for the project, which will be the case for many of my projects. We also explored numerous materials from woods, plastics, and settled on the reflective colored material. Stereoma is another installation that I designed and built in our lab. For me, installations are a training toward a work of permanence. And these first few projects that I'm presenting are not only important because of their interactive ideas, but from the growth and development between projects. Stereoma was initially conceived to support an exhibition and symposium on the topic of stereotomy 2.0. The exhibition featured design from prominent offices such as Zaha Hadid Architects and Foster Partners, to name a few. Each of the models had a custom framed catenoid geometry projecting light onto each of the models. I'm initially framing the lecture to be more technical and material focused, but in this case of the project, it's important to note the conceptual framework since it dictated the material selection, formal geometry, and lighting. The name stereoma takes influence from the Greek translation, which means the solid and unchanging place of the fixed stars, and the firmament translation, which connotes a thin veil-like layer that separates the heavens and sky as a vast dome. The installation creates an immersive and spatial experience using a vaulted, thin-like veil with custom programmed LED lighting. Constructed from mylar, the translucent and porous quality of the material created an ephemeral quality throughout the day and night, weaving both natural and artificial light throughout the gallery space. The LED lighting are controlled by a series of programmed Fade Candy and Arduino boards that run a sequence of image simulations across the surface, creating a lighting condition that changes color and brightness. Playing an animation of some of the lighting iterations that we went through in developing image patterns that went directly from a series of Arduinos to a series of strip lighting. The idea was to kind of work with different simulations, different lighting effects, control different patterns. We can move kind of quickly through this. This being the final version where we were going to beginning to blur the lighting, which giving us a more kind of solid more consistent light throughout the surface of the installation. Through forefarming software, an optimal hanging shape was engineered to create defined zones, which were specific to the work exhibited and allowed the work to be framed and viewed from any angle. This process is a departure from the Infinity helmet and adopted a quad-based mesh modeling process, which allowed for a more iterative method of working and a process that is adaptable to almost any spatial condition. The surface or veil was rationalized in 9 parts with 6 catenoid shapes connected to 4 stitched quad surfaces and realized by allowing the surface to be panelized with 1,200 discrete elements. The panels were organized, labeled, nested, laser cut, and assembled in the NYIT fabrication lab and designed with the intention to be flat packed, transported, and easily assembled on site. When I'm working on projects, I rarely produce representational drawing, but instead produce working drawings that go directly to the machine. It is not a drawing or shop drawing per se. It's a drawing that contains all the thresholds and range of that element designed for that piece, a panel or smart panel that has all of the parameters to become any part of the design. The second time the installation was installed in a gallery in Queens, New York. For the exhibition, the lighting was redesigned from the ground up and use a programmable super bright light package. I also want to note that the first installation was billed for under $800. This brings us to Kaleidos, an ongoing project collaboration between Pavlina Bardualake, the co-founder of Design Morphine, and myself, a project that was commissioned for a VR play lab in Manhattan. The company asked us for an interactive lighting installation that they could also use as a teaching device to teach programming to teens and kids, but also serve as an icon in their space when they had parties. The image we are seeing is from the bottom up, and you'll notice kind of a reference to materials from other projects. The conceptual response was our interpretation of a contemporary chandelier, complete with programmable and sensor-controlled LED lighting. The body would be constructed from custom fiberglass 3D printed nodes and fiberglass struts, clad in a unique variably curve-cut PETG plastic shell with unique CNC milled ceiling medallion. Our ideas were to dissect the unique ornamental parts of the historic chandelier and reinterpret them through unique material systems. Starting from the exterior shell, the initial idea was to introduce a material that would simulate the crystals that cover traditional chandeliers. The challenge was to stay true to the crystal's geometric material effect, so we began experimenting with PETG plastic for its flexible qualities, and knowing it's a great material for vacuum forming, but that did not solve the sparkle effect. So we began exploring cut patterns and considering using actuators to push the skin, and that proved to be a very daunting task. So I recalled a series of prototypes I made with my students that featured curve cutting as a method to deform and stretch a material beyond its means. Cutting kerf refers to the width of a cut. For example, on a table saw, it's the width of the blade. In our case, the width of a laser. We started with some known patterns that are accessible to download from the internet. Some of the early results were similar to expanded metal, for example. And then we were able to script some custom lines and patterns with the hopes the material would deform on its own or take a specific shape. You can see in the lower images how the line density changes or the length of line changes, for example. As we started working, we were taking sections of the exterior shell and developing subdivision strategies in Maya that we could deploy very basic curve cut patterns to begin a material feedback loop. The part that is interesting is that we're not simulating anything in 3D. We are working purely two-dimensionally, and through physical material manipulation, we start to understand what is capable from the cell subdivision and curve line density. And to date, we have cataloged a series of specific moves that, with the most successful being a double layered skin with one layer offset by 5%. Now I'm in the process of taking large unrolled panel sections and beginning to develop an animated process to cycle through curve subdivision strategies. Second layer is the framing system, which utilizes a custom scripted node and strut structure. Due to the geometry, not all parts are unique, but instead made up of 4 quadrants. The nodes are custom 3D printed, but the rods can be any off-the-shelf rod stock. So for example, wood, steel, fiberglass. After many years on and off streamlining this kind of node geometry system and the production workflow from understanding the length of the rods to ordering the rods in a spreadsheet to economize the off-the-shelf stock rod to minimize overall waste. For example, if you look at the number 1 rod, you will notice an out-of-order sequence in terms of the strut number. The script can take into account any material loss for cutting, which is really great for budgeting. This system goes back all the way to 2015 and was used on the Infinity helmet. Over the years, I've been able to incorporate additional hardware and print from a range of materials like plastic and metals and carbon fiber. Specifically in the case of this project, I'm 3D printing each node in carbon fiber since the machine is capable of printing parts as strong as steel. The great thing about the printer is the ability to define the regions which require more strength. In this case, the regions where the rods are inserted and the region where the cable will be inserted to hang the light. The next set of projects will further show how I'm using the strut node system to create a high-end custom furniture. The first example is the Astro bookshelf made from 3D printed stainless steel nodes and stainless rods. And we can see on the right, those are some of the stainless steel prints. A coffee table also using stainless steel nodes. The difference here is that this will take advantage of 3D printing wax parts for casting in bronze, which is a bit more economical. As I mentioned in the beginning of the lecture, would evolve from soft materials to hard materials, or from temporal to permanent, as the case of the coral table, which is a 3 meter by 1 meter solid one-piece marble table produced for the Marble Mock Stone exhibition in Verona, Italy in 2019. The design features a continuous woven minimal surface geometry fabricated in brown marble. The table design strategy generated a support system that takes its inspiration from landscape erosion and coral reef growth patterns with variable diameter members, creating a non-repeating, non-symmetrical, organic, and natural support structure. One of the challenges is the considerable amount of waste generated during the fabrication processes. But this is a one-of-one production. The table takes advantage of robotic fabrication by a company called Generelli, one of the best stone fabricators in the world. The challenge in production was finding a material that could withstand the demand of 16 hours of milling a day for 1 week straight, plus post-processing and finishing. The result was a flawless table that showcases the beauty of the natural material. Latest work in the final project I'll present is looking at how we develop workflows and methods to translate artificial intelligence text-to-image diffusion models to 3D models and eventually physically built projects. There's been an explosion of AI-generated images over the past few months, many of us using platforms like Midjourney or Stable Diffusion that convert text prompts to images. I believe these tools are game changers for all creative disciplines, and it's a matter of time before it's playing a role in everyone's design process. While I'm optimistic of the benefits, I'm also skeptical. Every tool is always up for debate and should be challenged, and we are already seeing that with text-to-image software. For example, who is the author? On the other hand, it's very exciting. It's a very exciting time to have a tool that can visualize your every dream or memory. For example, if you want a facade made of blown glass, or a lounge chair made from black marble and coarse leather, and even a pendant light clad with stained glass. As of a few weeks ago, we completed a successful translation from AI to 3D printed stone. The research investigation using language as a design method through these novel artificial intelligence tools and software. We collaborated with a 3D printing company specializing in printing upcycled stone and participating in 2 exhibitions in Verona, Italy for the Marble Mock Stone exhibition. There's an emerging opportunity to use AI to tap into the history of architecture in order to provoke possible futures of exploring form and ornament. The research uses expansive design practice to analyze Gothic elements and distort, split, and rearrange these elements to fit into a given space. But it's important to note the essential body is apparent, and to some extent the relationship to one another is maintained. Specifically, I was analyzing the key elements in Gothic design, such as the pointed arch, which led to the rib vault, flying buttresses, and the elaborate tracery. In order to achieve these images, a written set of rules were applied through the AI tool. First, stylizing as opposed to realistic representation. Second, schematic characterization by accentuating certain features. Third, dislocating split details. And fourth, an illogical transformation of details into new Gothic representations. The ambiguity of language is an essential part of the creative process when generating image iterations of these historic Gothic elements. The challenge of using these kind of new AI tools is in the output of a medium resolution image. In order to fabricate and realize these new representations, a workflow was developed in order to translate a 2D image to a 3D high-resolution relief model. We worked between a number of software, such as Shader Map, which allows us to create and edit high-resolution normal and diffusion maps. We then developed a workflow through Blender and Houdini and scripted the base surface outcome, which in turn allowed us to manually edit and sculpt the details. The final model appeared as a relief model, 3D printed in upscaled limestone. The final printed model in the exhibition formed a column with two different images, which were self-supporting multi-part prints with an overall dimension of 150 centimeters by 50 centimeters wide. Due to the constraints of the printer, we also had to split the surface into multiple unique parts. And the strategy was to try and follow the geometry the best we could to hide the seam lines. So we had the 3D file working directly with Concrete to optimize the mesh and surface resolution, and using their relatively new additive manufacturing process, developed 3D printed 4 unique images in limestone over the course of 2 weeks. Concrete's printers allow you to use powder and binder combinations previously unimaginable for 3D printing applications. What we're seeing now is the kind of complete workflow from the digital manipulation through the 3D printing process. So similar to maybe an old Z-Corp powder printer, the stone printer is laying down thin layers where it's then depositing a binder material. Completed, it has to be excavated. In the final imagery and the assembly process. And I would like to end on this slide and a comment that my work is striving towards a tight integration of concept, computation, and fabrication, tension between the physical and the digital. Instead of being separated into 2 stages, they are integrated into a process of feedback, an approach similar to a craftsman where material and making are all working in a process of feedback to yield a build project. Thank you.